Hidden deep inside the brutal maze of refrigeration fittings and industrial plumbing shelves across giant hardware warehouses worldwide sits a dense metallic cylinder with no electronics, no processors, and no external power source of any kind. Its price hovers around just $10. No subscription is attached to it. No corporation can remotely deactivate it during a winter energy shortage. Yet through nothing more than ruthless thermal conductivity and passive liquid circulation, this primitive chunk of naturally occurring metal can pull staggering quantities of discarded environmental heat out of the surrounding world and convert what would otherwise vanish into the atmosphere into a constant stream of residential hot water that costs virtually nothing. The massive $30 billion global water heater industry understands perfectly what this material is capable of. Their entire financial structure depends on the public never realizing how this cheap metallic component can be deployed using the uncompromising laws of thermodynamics. For more than a century, consumers have been conditioned to believe that producing hot water requires giant engineered appliances that either burn expensive gas continuously or devour heavily billed electricity every hour of the day. Fear became the foundation of the business. Fear of cold water, fear of running out, fear of independence from the utility network. What follows dismantles that manufactured dependency piece by piece. The real story is not about advanced electronics or futuristic machines. It is about raw heat transfer, passive flow physics, and an overlooked metallic conductor capable of redirecting wasted thermal energy already surrounding ordinary homes. Before revealing the exact metallurgical identity of this inexpensive object and explaining how it can be integrated into a residential system, the scale of the economic extraction surrounding modern hot water production must first be exposed completely. Every time a household faucet opens, an enormous hidden energy process begins operating in the background. The modern residential water heater has long been marketed as an engineering necessity, but in reality it functions as a monument to deliberate inefficiency and planned replacement cycles. That enormous 50-gallon steel tank humming quietly in a basement represents a continuous drain on household wealth. The entire mechanism depends on maintaining a huge reserve of heated water around the clock, even while the occupants sleep, leave for work, or disappear on vacation for days at a time. Water possesses an exceptionally high specific heat capacity. Raising its temperature demands an immense injection of energy. Utility companies capitalize on that reality by forcing electrical current through degrading resistance elements, or by selling natural gas to fuel combustion chambers underneath giant tanks. Meanwhile, thermal energy constantly escapes from the steel vessel into the colder surrounding environment. As heat bleeds outward, the thermostat activates repeatedly, cycling endlessly in a punishing loop of wasted energy and recurring cost. This is not accidental inefficiency. The tanks themselves are engineered with finite lifespans. Inside, a fragile glass liner and a sacrificial magnesium, a node rod temporarily shield the steel from corrosion. The moment that rod deteriorates beyond its functional limit, galvanic corrosion begins attacking the internal metal structure directly. Within roughly 8 to 12 years, the tank eventually ruptures. Flooded basements follow. Emergency replacements become unavoidable. Consumers are pushed directly back into the same expensive purchasing cycle once again. The entire arrangement operates like a carefully maintained economic trap disguised as basic sanitation infrastructure. Yet the system survives only because most homeowners never question the physics underneath it. To understand the alternative, modern plumbing assumptions must temporarily be discarded. The trail leads backward through history toward ancient thermal systems and forgotten off-grid engineering practices. Long before centralized utilities dominated residential heating, builders in multiple regions understood that ordinary human activity already generated enormous quantities of excess heat. Ancient Chinese Kangbed stove systems exploited retained thermal mass with remarkable efficiency. During the Back to the Land movement of the 1970s, independent engineers revisited similar principles while searching for methods to live beyond centralized energy dependence. Those builders recognized a simple physical truth the modern appliance industry rarely discusses openly. Everyday life constantly produces discarded thermal energy. Wood stoves warming a living room release huge quantities of residual heat. Compost piles generate intense internal warmth as organic material decomposes. Combustion exhaust systems throw valuable thermal energy directly into outdoor air, where it disappears unused. The true failure of the modern house is not a shortage of energy production. The failure lies in the architecture itself, which is designed to ignore and waste those thermal gradients entirely. The forgotten engineers of earlier eras searched for ways to intercept that escaping heat instantly, trap it efficiently, and redirect it into localized water supplies without relying on pumps or electrically powered circulation systems. Through careful manipulation of fluid density and temperature differentials, they constructed passive heating systems capable of self-regulating operation. No motors, no digital controls, no utility-supplied power. Only the relentless laws of thermal motion driving water naturally through conductive pathways. By exploiting the relationship between heated liquid and density reduction, they effectively created autonomous thermal engines built entirely from passive plumbing geometry. As water warmed, it rose naturally through the system. Cooler liquid descended automatically to replace it. Continuous circulation emerged without mechanical intervention. The process harvested ambient and waste heat that would otherwise vanish into the environment. Such systems represented a direct threat to expanding electrical and natural gas monopolies. As centralized utility infrastructure spread aggressively across residential construction markets, industrial lobbying organizations mobilized to standardize heavily controlled plumbing systems and commercial heating appliances. The economic incentives were overwhelming. A decentralized hot water method, requiring minimal purchased energy, offered little recurring profit opportunity for utility providers or appliance manufacturers. Over time, consumers were conditioned to view giant power tanks as the only legitimate solution for household hot water production. Passive thermal circulation systems faded from mainstream awareness. The knowledge survived quietly among off-grid builders, experimental homesteaders, and scattered thermal engineering enthusiasts, while the industrial market consolidated around increasingly expensive appliances dependent on continuous fuel consumption. Yet the underlying physics never disappeared. Heat still rises. Metal still conducts energy. Fluid density still shifts under thermal gradients exactly as it always has. And somewhere in ordinary hardware aisles, sitting unnoticed among refrigeration coils and plumbing stock, remains the inexpensive metallic component capable of exploiting those laws without requiring a single watt of purchased electrical power. Residential construction regulations were gradually rewritten with ruthless precision. The objective was simple: eliminate the architectural freedom required to build passive thermal circulation systems and force homeowners toward heavily regulated pressure tanks tied directly to centralized utility infrastructure. Expensive certified equipment became mandatory. Independent thermal designs were pushed outside legal acceptance. Step by step, the underlying science disappeared from public awareness, ensuring ordinary civilians remained financially chained to giant electrical and gas networks. Yet the laws governing heat and fluid movement never changed. Physics did not surrender to legislation. The survival method buried beneath decades of industrial suppression remains completely functional even today, and at the center of this forgotten system sits the same unimpressive metallic object mentioned earlier. That neglected $10 component hanging quietly in commercial hardware aisles is nothing more than a long, uninterrupted coil of soft Type L copper refrigeration tubing. Not rigid plumbing sections, not synthetic cross-linked PEX material, not complicated assemblies filled with moving valves or mechanical regulators. The entire principle depends on one continuous, pure copper pathway without interruption. The moment this specific metallic structure enters an intensely heated environment, the copper stops behaving like ordinary plumbing material and becomes an aggressive thermal transfer mechanism. Copper carries a thermal conductivity coefficient approaching 400 watts per meter Kelvin. In practical terms, it refuses to block heat. The material immediately absorbs thermal radiation from nearby surroundings and drives that kinetic energy directly into any liquid traveling through its hollow interior. But transferring heat into water represents only part of the equation. Without the second critical principle, the system would destabilize instantly. Water trapped inside the overheated copper would eventually flash into steam and rupture the tubing violently. This is where passive fluid dynamics transforms the entire concept into a self-sustaining engine. To create a continuous supply of off-grid heated water, the system must exploit the uncompromising mechanics of the thermosiphon effect. A closed circulation loop is formed. Cold water leaves the bottom of a large storage reservoir and enters the heated copper coil. Inside that extreme thermal zone, the liquid absorbs waste heat rapidly before returning upward into the upper section of the same reservoir. The driving force behind this circulation is not electricity. It is buoyancy, created through density differences inside heated fluid. The governing relationship is brutally simple. The pressure driving the loop equals the height of the system multiplied by gravitational force and multiplied again by the density difference between cold water and heated water. Gravity becomes the engine, density becomes the fuel. As cold liquid from the bottom of the reservoir enters the scorching copper coil, the water molecules begin expanding under intense thermal exposure. The fluid becomes lighter, less dense. The colder water behind it now possesses greater mass density and pushes forward aggressively. Superheated water surges upward through the top of the coil and races back toward the upper section of the storage tank, carrying free thermal energy entirely independent of the utility grid. That rising column of heated water creates another effect simultaneously. Near the bottom of the coil, localized low pressure forms naturally. More cold, dense water from the reservoir is silently drawn inward to replace the escaping hot fluid. The replacement water contacts the heated copper lattice, immediately absorbs thermal energy again, expands once more, and launches upward through the loop. The cycle repeats endlessly without pumps, motors, or electrical controls. At that moment, an autonomous thermal circulation engine has effectively been created inside the home itself. No expensive electric heating elements exist inside the system. No circulating pumps wait to fail mechanically. No metered natural gas lines feed combustion chambers. The entire process relies solely on fluid motion and thermal density exchange, performing the labor utility corporations have spent decades monetizing. The financial implications become staggering once lifetime operating costs are examined objectively. Consider the standard corporate solution first. A modern residential 50-gallon electric or natural gas water heater operating under average national utility pricing forces homeowners to spend approximately $600 annually in direct energy consumption alone. Stretch that cost across a conservative 10-year operational lifespan, and the energy expense alone reaches roughly $6,000, assuming utility pricing somehow avoids inflation, despite overwhelming historical evidence showing the opposite. Then the inevitable replacement arrives. Once corrosion destroys the internal lining and the tank structure finally ruptures, another major purchase becomes unavoidable. Replacing the weakened appliance commonly drains an additional $1,500. Over a single decade, the combined financial extraction reaches approximately $7,500 simply to keep household water from turning cold. Now compare that structure with the economics of the passive copper loop system. One continuous roll of soft Type L copper refrigeration tubing costs roughly $10. A heavily insulated salvaged plastic container or food-grade metal barrel functions as the reservoir and can often be sourced from local agricultural suppliers at virtually no cost. Basic brass compression fittings require another $5. The total projected lifetime expense for the complete passive thermal engine lands near $15, assuming the copper tubing is not physically damaged by external puncture. The mathematical difference becomes impossible to ignore. $7,485 separates the centralized corporate system from the passive off-grid alternative. This is not merely a clever budget trick or trendy internet experiment. According to the narrative surrounding these systems, it represents a devastating economic challenge to a deeply entrenched industrial market built around recurring consumer dependence. Anyone still questioning whether this engineering concept functions outside theory is directed toward the documented example of Silas Mercer, a retired fluid dynamics engineer with extensive technical training who lives entirely beyond the utility grid in the harsh, frozen wilderness of rural Idaho. Silas Mercer refused to surrender to the crushing propane delivery costs that repeatedly devastated families living throughout his isolated region. Standing on uncompromising principle, he chose not to participate in the expensive fuel dependency system surrounding rural survival. Drawing from decades of professional experience in fluid dynamics and thermal engineering, Silas engineered a complete escape from the commercial heating infrastructure. His attention focused on a massive source of overlooked biological heat. Deep within an active thermophilic compost mound, enormous thermal energy was being generated continuously through organic decomposition, a concept heavily associated with the work of French inventor Jean Pain. Rather than purchasing corporate manufactured propane heating systems, Silas assembled more than 50 feet of pure soft copper tubing with high thermal conductivity and buried the entire coil directly inside the hottest internal core of the decomposing organic mass. The copper lines extended outward from the compost structure into a heavily insulated water reservoir that operated entirely without electrical assistance. To guarantee uninterrupted thermosiphon circulation, the tank itself was positioned precisely 3 feet above the primary heat source. The geometry mattered. Elevation created the pressure relationship required for passive fluid movement. When winter temperatures across rural Idaho collapsed toward a brutal minus 20 degrees Fahrenheit, the internal biological activity inside the compost mound continued generating temperatures approaching 150 degrees through relentless microbial decay. Inside the elevated reservoir, freezing cold water naturally descended downward through the buried copper coil. The intense biological heat surrounding the tubing transferred directly into the conductive metal walls. The liquid expanded rapidly. Density dropped. Heated water surged violently upward through the return line and re-entered the holding tank at the top. Despite the lethal outdoor environment, the internal household water supply stabilized around 130 degrees. No electricity powered the process. No natural gas entered the system. Total metered utility consumption for residential hot water production remained absolute zero. Eventually, local inspectors arrived to audit the isolated off-grid property. Authorities reportedly assumed Silas must have been concealing illegal underground propane reserves to survive the region's deadly winters. Instead, what they discovered was a silent plumbing arrangement attached to a giant mound of decomposing wood chips and wet organic material. The system contained no hidden fuel infrastructure. No powered heating appliance existed to penalize. Silas Mercer had not stolen fossil fuels or bypassed utility meters illegally. He had simply exploited a thermodynamic weakness embedded within the entire centralized heating economy. A multi-billion-dollar industrial structure had effectively been circumvented using a $10 copper coil and naturally generated biological heat. But replicating such a system requires discipline and precision. Passive thermodynamic circulation cannot be assembled carelessly. Proper geometry, uninterrupted flow paths, and correct thermal positioning are absolutely critical for the system to function safely and effectively. Throwing random pipe beside a fire will not produce a stable thermal engine. The thermosiphon process depends entirely on elevation and continuous fluid pathways. The first requirement is identifying a reliable source of otherwise wasted ambient heat. During winter months, anyone operating a wood-burning stove already possesses a powerful thermal target. The blazing metal flue pipe venting combustion exhaust radiates enormous quantities of heat directly into surrounding air. Likewise, the active center of a large compost mound can serve as a biological heat core. Once the source is selected, the uncoated soft copper tubing must be wrapped tightly around the lower portion of the stove flue in multiple continuous layers, or buried in a spiral configuration deep inside the compost center, where temperatures remain highest. The objective is maximum surface contact between the copper and the thermal zone. Next comes the most mathematically important stage of the entire architecture. The insulated storage reservoir must sit physically higher than the copper heat exchanger itself. Specifically, the bottom of the water tank has to remain above the top of the copper coil. If the tank sits lower than the heating element, the cold, dense water will not descend correctly into the loop. Simultaneously, heated water loses its ability to rise naturally through the return pathway. Once circulation collapses, vapor lock forms and the entire system fails catastrophically. An insulated intake line rated for thermal exposure should travel from the very bottom of the water reservoir directly into the lowest connection point of the copper coil. From there, a separate insulated return line must extend from the highest outlet of the heated coil back into the upper quarter of the storage tank. That return path is critical. The line must rise continuously without dips, downward bends, or sagging sections. Even small low points inside the return tube can interrupt buoyancy-driven flow and stall circulation completely. Passive thermal movement depends on uninterrupted upward travel. After the plumbing network is assembled, the system is filled with clean, non-pressurized water.